Okay, we'll begin today, so please get settled in. So as you're all probably aware, it's exam week, the most wonderful time of the year. And if you have any last minute questions about the exam, please stop by and ask me if you're able to. I'll be in my office more often than not, definitely the rest of today and most of the week as well. Just a couple things about the exam that people have been asking. If you take the exam, you can see your score right away, but you won't be able to review the questions until Thursday evening. We could set up a time to go over your exam before then if you're really anxious to see what you missed. But in general, it'll be available for everybody Thursday evening after all the exams are finished. And then what occasionally happens is people miss their exam time slot for whatever reason. My strongest recommendation is to not let that happen, but if it does, it's not the end of the world if it's Monday or Tuesday of this week. So they do, at CASA, usually open up new time slots at night for the next day. So if you check between 7 and 11 p.m., they'll open up a few more seats for each exam slot for the following day. So if you miss your exam and it's a Monday or a Tuesday, then try to check back for open time slots for the next day. But I have no control over if that happens or when it happens, so you're kind of on your own for rescheduling if you do miss your exam slot. All right, but that's, I think, all I had to say about those logistics, so let's get right back into what we're talking about. So today we're going to start moving on towards the latter part of Chapter 4. Chapter 4 is all about structure and bonding, mostly in covalent compounds, and we introduced first VSEPR, which allows us to predict a three-dimensional structure. And then we talked a lot about valence bond theory and hybridization, which is sort of the theory that governs how these atoms are bonded together and rationalizes the shapes that we did predict. And then today we're going to finish up the things with valence bond theory and then move into a more complex but certainly more accurate bonding theory called molecular orbital theory. So to review what we talked about last time with hybridization, remember that we saw that hybridization involves mixing of atomic orbitals on the central atom. So very often when we're forming covalent bonds, and especially if we have shapes that are more complex than just linear, we have to invoke a mixing of the atomic orbitals on the central atom to allow those bonds to form in the correct geometry in these different structures that we predict. So hybridization deals with that. It's a mixing of the atomic orbitals, but the key point about valence bond theory is that the bonds formed by overlap of these orbitals with other hybrid orbitals or atomic orbitals. But something we'll have to keep in mind as we start introducing molecular orbital theory later today is that when you have valence bond theory and you have hybridization and all those ideas, we're still talking about very much localized orbitals. So you'll have a hybrid orbital that's localized on the central atom, and then you're going to have another hybrid orbital or atomic orbital that's localized on the atom that it's bonded to, and then those two localized orbitals are going to overlap to form a bond, but they still very much are attributed as belonging to one atom or the other. So there's still sort of two orbitals involved in forming the bond, and that's more of what we call a localized approach, which we'll contrast today with the delocalized model called molecular orbital theory. And then as I already said, the hybridization accounts for these VSEPR shapes because we know that the valence p orbitals that are typically present in these types of atoms and these types of elements, those valence orbitals are oriented at 90 degrees to each other. So if you want to have more complicated shapes like tetrahedral, like trigonal bipyramidal, all those things, you need to hybridize the orbitals to orient them in the correct positions to be able to form bonds in those directions. So it accounts for that VSEPR shapes that we predicted, which is more of a geometric approach. And then we saw last time that there's basically 5 types of hybridization we'll see, and it really depends on the steric number. So the steric number being the total number of electron groups, which we know can range from 2 up until 6. That's as high as we're going to talk about, and really as high as you'll see in real molecules. And each of these then correlates with a specific hybridization, sp, sp2, sp3, sp3d, and sp3d2. All right, so if we know the steric number of our central atom, the number of electron groups that are around that central atom, we can then predict the hybridization very easily. But there are some details that we have yet to leave out, and that's what we're going to get to today. But first, let's just do one quick one to practice how to determine hybridization. So let's We have a guest speaker today, Roman.
Yes, I may have lost my...
Is it this?
No, the things I don't see it. Transmitter. That's the only one.
Alright.
Yes, it's now.
Okay, sorry. We'll continue on with this example problem. So predict the hybridization of the central atom in IF3. And so like many things we're doing in Chapter 4, it requires us to draw a good Lewis structure. Lewis structures are really a Chapter 3 topic, but without them we can't say anything about the shape or the hybridization of the molecule that we're interested in. So we have to do the Lewis structure for these ones, IF3. So each of these is in group 7. These are halogens, so they each contribute 7 valence electrons. So the central atom contributes 7 valence electrons, and then the fluorine contributes 7 as well, 3 of them though. So we have 28 valence electrons. And then so when we draw the Lewis structure, we start with single bonds. And that's what we should get. So we start with single bonds, we complete the octet, that's 24 electrons. We have 4 more that go in the central atom as lone pairs. So then, again, for predicting hybridization, the key parameter is the steric number, or the total number of electron groups. And remember that the steric number is the number of things that are attached to the central atom. And we count a thing as being an atom, whether it's singularly, doubly bonded, or multiply or triply bonded, it's just one thing. And then each pair of electrons counts as an electron group. So remember that we're talking really about the arrangement of orbitals around the central atom. So we can put 2 electrons into an orbital, so we count each pair as one electron group. And so in total then there's going to be 5 for this one, because we have the 3 fluorines and the 2 pairs of electrons. 3 plus 2 is 5. And so if we have 5 things bonded to the central atom, the hybridization then has to be as follows. We list all the orbitals that could be involved in hybridization. Remember, as we saw, the central atom has a single s orbital, it has 3 p orbitals, and it can hybridize up to 2 of its d orbitals. And so if we have a total of 5 electron groups, we need to hybridize these first 5 orbitals here, which gives us sp3d. All right, so predicting the hybridization is really simple once you have a good Lewis structure, and there's really no more to it. But there are some additional details of valence bond theory which we'll also need to be aware of when we move into molecular orbital theory that we haven't talked about yet, and that's really the type of bonds that form. So all the examples that I've shown you with hybridization so far, and you know, last time we went into some detail about how the orbitals rearrange themselves and the energies of those orbitals. We were only dealing with single bonds. You know, the outer atom to the central atom has a single bond. What happens if we have multiple bonds? And when we have double and triple bonds, we need to consider the possibility that there's really 2 types of bonds that can form when we overlap atoms in a covalent fashion. So the one that's more straightforward, and we kind of already drew a bunch of pictures of this last time, is sigma bonds. So to give you a precise definition of a sigma bond, so we're adding more Greek letters to our vocabulary now. This is sigma, and these are bonds that are formed by end-to-end overlap of orbitals. And they can form from either atomic or hybrid orbitals. And when we have these sigma bonds, the electron density, so remember that any type of covalent bond involves shared electrons, and those shared electrons, the electron density of that bond is going to be greatest in between the nuclei along the axis of the bond. So all the pictures that I at least attempted to draw last time that involved orbitals overlapping, either atomic orbitals or hybrid orbitals, those were all sigma bonds that I was drawing. And so the orbitals can be atomic or hybrid. We can form sigma bonds with any of these types of orbitals. So we don't need to have hybridization to form sigma bonds, but very often hybrid orbitals are involved. And another key point is that If the central atom is hybridized, which it will be in almost every situation, those hybrid orbitals that are localized in the central atom, those will only form sigma bonds. So we're going to learn about two different bond types, and the second one's coming up here in a second. But if you have hybrid orbitals on the central atom, those will only form sigma bonds. All right, so that's an important point. And then when we draw pictures of these, it's very similar to the pictures that I drew last time, or identical really. So you could have two s orbitals overlapping. So if we have, let's say, 1s and 1s overlapping, remember that what happens is that you get this sort of overlap that's in between the nuclei. So these little dots here that I'm drawing are the nuclei. And then you have this overlap region that's in between the nuclei that sort of classifies it as a sigma bond. Okay? So when you have overlap right between like that with the two orbitals coming head to head together, that's a sigma bond. You can form sigma bonds with p orbitals or sp hybrids as well, which look very similar, but in this case, so again, the nucleus is right there at the center of the orbital, and if we overlap two of these, we can also form a sigma overlap, which is this end-to-end overlap where the two orbitals sort of come face to face and overlap in between the two nuclei. All right, so nucleus is there, and then overlap region again in the center between the two nuclei. All right, so that's what we mean by a sigma bond. They have sort of cylindrical shape, and the electron density is between the two nuclei. Now there's another type of bond that's involved, and this is only going to show itself when we have multiple bonds, either double or triple bonds, and these are called pi bonds. Okay? So pi bonds, as opposed to being an end-to-end overlap, these are a side-to-side overlap of orbitals. All right? There's more precise definitions that you may learn in more advanced chemistry courses, but for our purposes, a pi bond can be thought of as a side-to-side overlap and what this results in is regions of electron density above and below the bond axis. So the shared electron density is not in between the nuclei, it's kind of above and below the nuclei this time. Okay? So side-to-side overlap above and below the bond axis. And the only types of orbitals from our standpoint that are going to form pi bonds are unhybridized p orbitals. Alright, so as I said, hybrid orbitals will only form sigma bonds, and any unhybridized p orbitals that you have could be involved in pi bonding. Alright, so as we saw in some cases, when you have sp or sp2 hybridization, you're going to have one or more unhybridized p orbitals on the central atom, and those unhybridized p orbitals could be involved in forming pi bonds in the situation where those occur. D orbitals can also form pi bonds, but we won't learn about that in this course. It's a very interesting topic, but one that we just don't cover in general chemistry. But if you take my other courses I teach, you'll hear all about that. All right, so unhybridized p orbitals are involved in forming pi bonds, and like I said, it's above and below the bond axis. So here you're taking two p orbitals and you're lining them up side by side, not end to end. And you form an overlap that sort of looks like this. So you have your bond axis between the two nuclei, and then the overlap is above and below. So you have sort of overlap above and below like that, that's sort of holding them together. All right, so that's what a pi bond looks like. The shared electron density is above and below the axis of the bond, not along the axis of the bond like it is in sigma. Okay, so those are the two types of bonds. And again, it's helpful to understand what they look like and the orbitals that are involved in forming them to get a little bit more directly at what you're going to have to be able to do for homework and test problems. What we're often going to ask you to do is predict the number of sigma and pi bonds that are involved in forming the bonds for a structure. So if we're using valence bond theory, which is just this idea about hybridization and using Lewis structures to predict the bonding as we've been doing, then if we have single bonds, all single bonds are going to be sigma bonds. All right, so if we're looking at a Lewis structure and there are single bonds in the structure, as there almost always are going to be, then all of these single bonds are going to be sigma in their bond type. All right, so if you look at any single bond in a structure, it's going to be sigma. Now, one thing we didn't talk about last time when we introduced hybridization is what happens when there's multiple bonds, so double bonds or triple bonds in structures. Multiple bonds will always consist of one sigma bond. All right, so one of those 2 or 3 bonds is going to be sigma, and the rest are going to be pi bonds. And so again, since we're only talking about p-block elements and covalent compounds involving p-block elements, then we don't really have to consider all these different possibilities. We really only have either double bonds or triple bonds. So if we have a double bond, as we said, in a multiple bond, one of those bonds is a sigma, and the rest are pi. A double bond only has 2 bonds, so it's going to be 1 sigma and 1 pi to form a double bond. And then if we have a triple bond, you're going to have 1 sigma, and then the other 2 bonds are both going to be pi. A sigma and 2 pi bonds makes a triple bond. Okay, so as we've already talked about, double bonds means you're sharing 2 pairs of electrons. Triple bonds means you're sharing 3 pairs of electrons. When you have a double bond, one of those electron pairs is shared in a sigma fashion, and those are typically going to be involved orbital overlap of hybrid orbitals. And then the other bond is a pi bond, where you're going to have unhybridized p orbitals that overlap above and below the axis of the bond. So do I have any? I don't have any pictures of this later on. So to draw a quick picture of this, if you have this molecule up here, I'll draw it up here. Call it ethylene. Very simple organic molecule with a double bond. So if we have this molecule here, each carbon is sp2 hybridized. Each one has 3 things attached to it. And so then the sigma bonds are going to be involving those sp2 orbitals. So you would have each carbon is sp2 hybridized. And then it's going to form overlap with the other carbon atom. So that's going to be your sigma bond here, which involves sp2 orbitals. And then you're also going to have a pi bond. So this is a double bond, so you're going to have 1 sigma and 1 pi. And remember that when you have sp2 hybridization, you still have p orbitals that are unhybridized. And those p orbitals are going to be perpendicular to the plane of perpendicular to the trigonal plane, and they're going to overlap above and below that trigonal plane. So that's going to be your pi bond, which is a 2p overlapping with a 2p. All right, so this is sort of how the picture of it looks. You're going to have, when you have a double bond, you have a sigma bond that involves the hybrid orbitals, and you have pi bond. There's a pi bond that's going to involve the unhybridized 2p orbitals. So for the other examples that I gave you for sp2 hybridization, these unhybridized p orbitals are not necessarily going to be involved in the bonding, but in many cases they will form pi bonds, as we see in this compound here. Okay, so that's sort of the picture of what it looks like. But like I said, the more important thing you're going to have to do is be able to count the number of sigma and pi bonds that are in a... Okay. All right, so let's do an example of this. How many sigma and pi bonds are in the organic molecule below? All right, so I drew the whole structure. All the bonds are filled in. You don't have to fill anything else in, but we want to know how many are sigma and pi. So remember that every single bond is a sigma bond. So we can go through and write sigmas next to all the singles. So every CH bond is a single bond, also is going to be sigma. And then we have a bunch of CC single bonds as well. And then we have a bunch of multiple bonds in the structure, which I'll label in blue. And then remember, for each multiple bond, they will have 1 sigma bond, and the rest are pi. So this double bond is going to be 1 sigma and 1 pi. This double bond is going to be 1 sigma and 1 pi. And then this triple bond is going to be 1 sigma and 2 pi's. Alright, so I hope I didn't forget any bonds, but you look at each single bond and put a sigma next to it. Each multiple bond is a sigma with rest pi. and now it just becomes an exercise in counting. So assuming I can count correctly, I think I got 15 sigmas and 4 pi's. All right, so there are 19 total bonds in this molecule, and 15 of them are going to be sigma, and 4 of them are going to be pi. Okay, any questions on how we got that? All right, so now we're going to move on to molecular orbital theory. If you'll give me a second here, I'm going to try to pull up a video that I'm going to look at. So I might, and I forgot to do this before class. Let's see if I can highlight this. I don't think it's going to work. Let's see. I kind of want to show you guys this, and I forgot to pull it up before class. Alright, sorry for not being more prepared. Okay, so we'll get to this in a second, but let's first introduce what the problem is here. So we've talked about valence bond theory, which is the idea of hybridization, all these things we've been talking about, the sigma and pi bonds. And for most things, it works very well. So you're going to use, when you guys take organic chemistry, if you do in the future, you're going to use valence bond theory all the time. And it predicts a lot of things about molecules that are, quite useful and quite accurate. But it, of course, has some problems with it, as any theory does. And so the big problem with valence bond theory is that sometimes certain predictions about the properties of molecules just are not correct. So let's look at the example of O2 here. So if we draw the Lewis structure of O2, what you would get is this structure here. Each oxygen contributes 6 valence electrons, and when you complete the octets, you get a double bond and 2 lone pairs for each oxygen. So a pretty simple Lewis structure for us to draw. We would predict from valence bond theory that it has a sigma and a pi. Now, valence bond theory assumes then that all of these electrons are paired. So you would have the electrons that are shared in a bond are going to be paired, spin up, spin down. Then you have these lone pairs that reside in the other sp2 orbitals, and they have to be paired, spin up, and spin down to not violate Pauli exclusion principle. So we would predict from the Lewis structure of O2, and by using valence bond theory, that there are 0 unpaired electrons in O2. Okay? So when you draw Lewis structures, you assume that all of these lone pairs are in fact paired electrons with one spin up and one spin down, so you count there's no unpaired electrons in this case. So then we can predict the magnetic properties. We're going to talk more about magnetic properties later, but this, whenever you have 0 unpaired electrons, it's what you call diamagnetic. Which means that the compound will be weakly repelled by a magnetic field. All right, so there are 2 basic magnetic properties. But diamagnetic means it has very little interaction with magnetic fields, but would be weakly repelled. Paramagnetic, which we'll talk about later, means that it's attracted to a magnetic field. All right, so then we have this prediction for valence bond theory. Let's see what the actual properties of oxygen are. So we're going to play this video.
So when I pour the liquid oxygen between the poles of the magnet,
and pour it through a very strong magnetic field.
It sticks.
Oxygen. And you see that the oxygen sticks in
and we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Suspended between the 2 magnets, so it is attracted to the magnetic field, which is not what we would predict from valence bond theory, which says that it should be weakly repelled by the magnetic field. Okay, so that's what we see for liquid oxygen. And I believe the next one he's going to do is nitrogen.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Now they're going to take liquid nitrogen and do the same thing. see that liquid nitrogen goes right through
hey.
the magnetic field.
More.
So there's so oxygen sticks to the magnetic field, it's attracted to the magnet, and then your nitrogen.
There's the good one.
That's also oxygen. But the one thing she poured through that went straight through was nitrogen. Possibly nitrogen also, but I must be wrong. All right, but anyway, oxygen is the important one there. So when we look at oxygen, I should probably close this or just start playing other videos without me asking it to. All right. So what actually happens, what we saw in that video, is that O2 was attracted to the magnetic field, which must mean that O2 is paramagnetic. And this is basically the scientific method at work. We had a bonding theory, a valence bond theory that we thought was pretty good, but then you do an experiment that runs counter to that theory, and that must mean that the theory is not quite right and needs to be refined. And so the theory that came about later on, which then allowed us to make more accurate predictions about the electronic structure of molecules, is called molecular orbital theory. All right, so if valence bond theory doesn't correctly predict that O2 is paramagnetic, we need a new theory that would predict that as well. So that's where we get to what's called molecular orbital theory. And this is one of the more complex topics we'll get to in this course, but as we'll see, the types of questions we'll ask you about it are not too in-depth. All right, so the idea of molecular orbital theory is that we still have a mixing of atomic orbitals, but here what we're doing is we're taking atomic wave functions from two different atoms and mixing them together. And this is the key difference between molecular orbital theory and valence bond theory. So for molecular orbital theory, we're taking atomic wave functions, atomic orbitals, and remember that these wave functions are just mathematical functions, and we're going to combine those mathematical functions in different ways. All right, and so what we're going to do is we're going to take linear combinations of atomic orbitals, which basically means we're going to add and subtract them from each other. All right, but the key difference between molecular orbital theory and valence bond theory is that these orbitals that we're forming are delocalized. So we're taking two atomic orbitals from two different atoms, we're mixing them together mathematically, and we're making a new wave function that is delocalized over both of those atoms. It includes both of the atoms in the bond. It's not just localized on one atom or the other, it's a delocalized molecular orbital. In valence bond theory, we have hybrid orbitals that are localized on the central atom. In molecular orbital theory, we have molecular orbitals that are delocalized over the entire molecule. Now, molecular orbital theory gets very complicated for anything beyond a linear structure, so we're only going to talk about very simple diatomic molecules in the context of this theory, but if you take more advanced chemistry courses, you'll get into a lot more details about molecular orbital theory of much more complex species. All right, so when we mix atomic orbitals, we can't just mix any two orbitals. There's some considerations that we have to follow here. So one is that only the orbitals that are close in energy can mix. All right, so that's an important point about which orbitals we can mix together. All right, because you might think of some more complex species, like let's say we have, two phosphorus atoms bonded together. Each phosphorus has 1s, 2s, 2p, 3s, 3p orbitals, and then you can make combinations of all of those. That's a lot of combinations, but only the orbitals that are actually close together in energy will mix with each other. So really it's only the valence orbitals from one atom mixing with the valence orbitals of the other atom. The other orbitals that are the core orbitals are going to be too low in energy, and they're not going to really contribute to the molecular orbitals. So just like we saw for every other bonding theory we've talked about, we just need to consider valence orbitals. All right, the core orbitals are too close to the individual nuclei. They're not able to mix very well with the other core orbitals, so we only need to consider the valence orbitals. So when we mix these orbitals together, we have two possibilities. We're doing linear combinations of orbitals, and we have what are called bonding and anti-bonding orbitals. So for a bonding orbital, which we abbreviate as psi, so psi is still the abbreviation for wave function, we're going to do an additive combination of two atomic orbitals. So the atomic orbital from one atom is going to be added to the atomic orbital from the other atom to give us a new bonding orbital which is an additive combination of the two. Alright, so this is going to be a delocalized molecular orbital, and it's going to be an additive combination of the two individual atomic orbitals. Now when we're mixing two atomic orbitals, we can do the additive combination, which is the in-phase combination. Remember, these are wave functions. Or we can do the subtractive combination, which is the out-of-phase combination. So the other one, which is out of phase or subtractive, we call the anti-bonding orbital when you abbreviate it with a little asterisk, psi star. Okay? And that's going to be the subtractive combination of the two, AO1 minus AO2. And we call this the out-of-phase combination. Okay? So then these two different combinations of orbitals, the bonding and the anti-bonding, have different electron density arrangements, as we'll draw pictures of later on, and they have different energies. So for a bonding orbital, the electron density is greater along the bond. And so a bonding orbital increases the overlap of the electrons between the two nuclei and increases the strength of the bond. And then the anti-bonding combination, you have electron density that's greater outside of the bond, or outside the internuclear region. And so as we'll see, when you put electrons into anti-bonding orbitals, you're sort of pushing the two nuclei apart and you're weakening the bond or making them farther apart. And then the energy of these two orbitals, so what we're going to be doing here is mixing atomic orbitals and making a new set of molecular orbitals and ranking them in terms of lowest energy to highest energy. The bonding orbitals are lower in energy, so these in-phase combinations result in orbitals that are lower in energy than the atomic orbitals. And then this out-of-phase combination results in energies that are higher than the individual atomic orbitals. Okay? So that's sort of the basics of what we're doing. So now we can start talking about the shapes of these orbitals as well as an energy level diagram when we mix two together. So we're going to start with the very simplest case, which is mixing two 1s orbitals together. So in the simplest situation where we only have one valence orbital on each atom that we're mixing together, so something like H2. So if we're going to take two 1s orbitals, one on one atom, one on another atom, and mix them together to form molecular orbitals, what does that look like? So 1s orbitals, as we learned in just earlier today when we talked about sigma and pi bonds, 1s orbitals can only form sigma bonds. So one of the molecular orbitals that we form, we're going to label as sigma, and that's going to be the additive combination of the two 1s orbitals. Now the key difference here, as I said, is that we're not forming, it's not two individual orbitals anymore, we're forming a new additive combination that's delocalized. So what this would look like then is you have your two orbitals, your two nuclei here, and then your orbital is going to be delocalized over the entire molecule. So if this is, for example, H2, you have a sigma molecular orbital that's delocalized over the entire molecule. It's just one orbital that belongs to the entire molecule. You no longer have individual atomic orbitals at each hydrogen. That's what we do with molecular orbital theory. Now if we have this additive combination, which we call sigma 1s, we also have the anti-bonding out-of-phase combination, which we call sigma star. And we put a little 1s in subscript to tell us that it comes from a combination of 1s orbitals. And this is going to be the subtractive combination, 1s minus 1s. So what we have here then is the two nuclei, and we're adding the orbitals out of phase. And so remember that when we draw pictures of orbitals, we indicate the phase with different colors. So we have electron density with one phase near this nucleus. We have electron density of another phase near this nucleus, where we've done a subtractive combination of those, and then we have a node in between. And we call this, so remember this one's called bonding, and this is called anti-bonding. Okay? So that's our sigma 1s bonding orbital, where we have electron density between the two nuclei, And then our anti-bonding orbital, we mix the two 1s orbitals out of phase. And anytime you change phase, you have to have a node there, and there's no electron density between the two nuclei when an electron sits in that orbital. Okay, so that's what they look like. And then what we're going to be mostly interested in this course are the orbital diagrams. So we have, the way we draw this is we have two 1s orbitals. So we're mixing these two atomic orbitals. And then, like I said, we mix them in two different ways. We form an additive combination, which is sigma 1s, and that's going to be lower in energy. So the center part of our diagram are the molecular orbitals, and then we have the out-of-phase combination, which is higher in energy. So the electrons in our molecule are no longer going to belong to these individual atomic orbitals. They're going to be filling these molecular orbitals that we form by mixing the atomic orbitals together. And a key point when you're drawing orbital diagrams or looking at them is that the number of atomic orbitals that we combine together has to equal the number of molecular orbitals that we form. So there's not really a law that's called this, but you can think of this as the law of conservation of orbitals. So if we mix two 1s orbitals together, we're going to form two molecular orbitals. One is going to be bonding, it's going to be lower in energy. One is going to be anti-bonding, it's going to be higher in energy. And then, so the idea here is that when we have molecular orbitals, we can think of, okay, how many electrons are in our molecule, and then we fill these orbitals from lowest energy to highest energy, just like we do when we're filling atomic orbitals. So we figure out the ordering of the orbitals from lowest to highest, and then we mix, and then we just add the electrons in until we've added all the electrons that we have. And so when you're just mixing two 1s orbitals, it's a very simple picture where you have a sigma and a sigma star orbital being formed. So once we fill these with electrons, which we're going to do here in a second, we then have a few different parameters that can be determined from the molecular orbital diagrams. So we can predict bond order from valence bond theory, where we use the Lewis structures and the formal charges to predict whether it's going to be a single, double, or triple bond. And we can also predict that from the molecular orbital diagram. So we take the formula for this is going to be 1/2. We count the number of electrons that are in bonding orbitals, and we subtract the number of electrons that are in anti-bonding orbitals. So as I said, when we populate bonding orbitals, we're strengthening the bonds. And when we populate anti-bonding orbitals, we're weakening the bond. And so we take 1/2 times the difference of those, and that's going to give us the bond order. Which, now the nice thing is that the bond order that we predict from valence bond theory is going to pretty much always be identical to the bond order we predict from molecular orbital theory. But as we'll see, we can use molecular orbitals to predict fractional bond orders of 1.5, 2.5, and so on, that are not as easy to rationalize using valence bond theory. So it is a more powerful approach in that regard. We can also predict the bond type, so depending on which types of molecular orbitals are filled, we can predict whether they're going to be sigma, pi, or some combination of sigma and pi involving in the bonding. And then the key one here, which is sort of what I introduced as why we even need this theory in the first place, is that we can now accurately predict the magnetic properties. So as I said, valence bond theory predicts diamagnetic for O2, which means no unpaired electrons. But if we use molecular orbital theory, we will correctly predict the magnetic properties each time. So the two magnetic properties that we can have are diamagnetic, which means no unpaired electrons, and the behavior then that we observe experimentally is that these are weakly repelled by a magnetic field. And then if we have paramagnetic, this is a situation where we have one or more unpaired electrons. And as we saw for liquid oxygen in that video here, these are going to be attracted to the magnetic field. All right, so this is probably the most powerful aspect of molecular orbital theory, is that we can now accurately predict the magnetic properties of molecules, which we cannot do with valence bond theory. All right, so with those in mind, let's start looking at some real examples of molecules and then how we build their molecular orbital diagrams. So we're going to start with the simple ones, which I've already introduced, which is just going to involve mixing of 1s orbitals. All right, so if we have anything with hydrogen in it, remember that the valence orbitals in hydrogen are 1s. Those are the only valence orbitals in hydrogen. And so we're only going to be able to mix those two orbitals together. So if we have H2 plus, we're going to take a 1s orbital on the first hydrogen, a 1s orbital on the second hydrogen, and we're going to mix them together. And just like I showed you, you're going to form a sigma 1s and a sigma star 1s. And so when we fill these orbitals up, we fill them from lowest to highest energy. So how many electrons does H2 plus have? So H2 would have 2 electrons, then how much would H2 with a plus charge have? 1. So each hydrogen contributes 1 electron, but then we lose 1 for the positive charge. So this is only going to have 1 single electron, and so of course that electron is going to go into the lowest energy orbital, and so we have this sort of diagram here. So if we write the configuration for H2 plus, it's going to be sigma 1s1. So just like we saw for atomic orbitals, we can write electron configurations involving molecular orbitals, and in this case it's going to be sigma 1s1. If we want to calculate the bond order for this, remember the bond order is 1/2. We count the number of electrons that are in bonding orbitals. So this is our sigma 1s bonding orbital. There's 1 electron there. We subtract the number of electrons that are in anti-bonding orbitals. The anti-bonding orbital is empty, so there are 0 electrons up there. And so we predict a bond order of 1/2. And so again, by using molecular orbital theory, we can predict fractional bond orders, which is not something that's easy to do with valence bond theory, which assumes that all the electrons are paired when you form a bond. If we go to simple H2 now, H2 has 2 electrons, 1 electron from each hydrogen. We mix the 1s orbitals together. We make a sigma 1s and a sigma star 1s. And then we fill these orbitals lowest to highest energy. So the lowest orbital is sigma 1s. Just like we saw in atomic orbitals, each orbital can hold up to 2 electrons. And if they have 2 electrons, they have to be spin paired like that. And so the configuration for H2 is sigma 1s2. So we've now put both of those electrons into the sigma 1s orbital. But because of Aufbau principle, we fill the sigma 1s before we start adding electrons to the sigma star. If we calculate the bond order for H2, 1/2, we take the number of electrons that are in bonding orbitals, which is now going to be 2. Both of these electrons are in a sigma 1s bonding orbital. We subtract the number of electrons that are in the anti-bonding orbital, which is still empty, so 0. And we predict a bond order of 1 for H2. Just like we would if we were to draw the Lewis structure for H2, which just has a single bond between the 2 hydrogens. So no difference there. But this predicts a single bond for H2 with a configuration of sigma 1s2. And then if we have H2 minus in He2, we would have the same basic diagrams. We're still mixing 1s orbitals, so we're still going to form a sigma 1s and a sigma star 1s. This would also be the same diagram that we would get for He plus. So both of these have 3 valence electrons. So if we add 1 electron to H2, or we take 1 electron away from He2, we would get 3 valence electrons. And so now when we add 3 valence electrons to this diagram, we fill the lowest energy orbital first with a pair of electrons, and then we have to put our 3rd electron up here into the anti-bonding orbital. Same exact rules that we follow for filling atomic orbitals, lowest to highest, pair the electrons if they're in the same orbital, and so on. So the bond order here then is going to be 1/2. We have 2 electrons in the bonding orbital. We have 1 electron now in the anti-bonding orbital, sigma star 1s. And so again, for this one, we predict a bond order of 1/2. So another prediction that results in a 1/2 bond order. And then finally, if we do He2, so the configuration for this one would be sigma 1s2, sigma star 1s1. Okay? So if we want to write the configuration out, we have 2 electrons in our sigma 1s, 1 electron in our sigma star. That's how we would write it, just like we do for atomic configurations where we'd have 1s2, 2s2, so on. Okay? And then finally, the last one that I'll give you is He2. So He2 has 4 valence electrons. Each helium has 2. It's atomic number 2 in the periodic table. So the only orbitals involved are 1s again. So we form a sigma 1s and a sigma star. Now we have 4 electrons to put into our diagram. Each orbital can only hold 2, so we put 2 there and 2 there. And then if we predict the bond order for this case, we have 1/2. We have 2 electrons in our bonding orbital. We also have 2 electrons in our anti-bonding orbital, so 2 minus 2 is 0. Now, what exactly does it mean to have a 0 bond order? We can't just, stop here and assume this means nothing. So when you have a bond order of 0, that means there isn't a bond at all. And so that means He2 is unstable, or another way to say that is that it does not exist at all. So whenever you predict a bond order of 0, it means that the molecule doesn't form a bond and it doesn't exist. And so we would predict that noble gases don't form bonds with each other, and the molecular orbital diagram rationalizes that because we've completely filled the bonding orbital, we've completely filled the anti-bonding orbital. Those two cancel each other out, and we have no net bond in this molecule. So next time we're going to get into more complicated orbital diagrams when we start involving p orbitals, and we'll see how that works for the p block elements as well.